Welcome back to Industrial Automation course, Lecture 16, Continuous Function Chart CFC Programming in Codices. Today's topics are as follows. Continuous Function Chart CFC Programming, Cursor Positions in CFC, CFC Elements Toolbox, Example of Composer, Example of Selector, CFC Programming Example, and CFC Programming Exercises. Useful video tutorials. Suggested video tutorials from YouTube are as follows. I strongly recommend you to go through these extra videos to learn more about CFC programming in general and in codices. Continuous Function Chart CFC Programming. Continuous Function Chart CFC is an extension to the IEC 61131-3 programming languages. Okay, so it is basically a standard language of IEC. The CFC editor, in contrast to a network editor, allows free positioning of the elements, which, for example, allows direct insertion of feedback passes. The sequence of processing is determined by a list which contains all currently inserted elements and can be modified. Okay, so we don't have network as we used to have in ladder logic programming, but we have float box that it's very similar to simulation in MATLAB. So if you've done simulation in MATLAB, you will find it very similar to those type of environment. And that's why, for example, you could implement feedback passes like PID controllers in MATLAB. You can connect the input and output pins of elements by drawing a line with the mouse. The color of a line may indicate its data type if configured in the options CFC editor. So as you could see, we have one example here, and you see boxes floating around, and you could connect the output of one box to input of the other by lines and connection. Again, very similar to MATLAB simulation environment, if you are familiar with those type of environment, if you work with that in linear control theory courses and labs. CFC is based on the free body diagram language. However, in contrast to that, no networks are used, but free positioning of graphic element, which, for example, allows feedback loops. So you could see one example here, and you see the definition of all variables here in this function block. We will go through some examples, and you will do the programming by yourself. So this is basically one example. So once you want to write a function block, if you choose a CFC in codices, when you choose a CFC language as a programming language, then you will see this type of environment. Okay, so either in the main PLC program or in function block, you will see this type of environment with this element here. And these are our inputs, boxes, and outputs and connections. It might happen that the elements get positioned in a way that they cover already routed connections. So for example, here you say that it goes through one box. These collisions, so we have a collision between the line and the box, are indicated by red shadowed connection lines. If there are any collisions in the chart, the bottom in the upright corner of editor view gets a red outline. Okay, so this button. So you see that we have collision here, and this bottom now, it has a red outline. When there is no collision, the icon is green. So you should always program in a way to see this green bottom here instead of red. And if we see the red one, we need to clear these collisions. Don't worry about these inputs output boxes, where this coming from. We will see in coming example, but for now, this is just introduction to the CFC, the environment, and uh, basically what is exactly the programming environment, connection between elements, and so on and so forth. When there are several collisions, to edit the collision step by step, click on this button and use command show next collision. Then each the next found concern connection will be selected. So when you click this one, the first one appears, you need to sort it out, and then click again next, and then we'll jump to the next one, and you need to clear that collision as well. For complex charts, you could use connection marks instead of lines. So you could right click, for example, on this line if there is any collision. Even if there is no any collision, you could this method, okay? It's up to you. But usually when there is a complex program and lots of collision and it's hard to clear those collisions, it's good to use this method. So you basically right click on the line and you will choose connection mark. Once you do so, the program automatically will put these connection marks. You could change the name to, for example, whatever names you wish, but as a default, it starts with C1, which is a connection mark 1. Or alternatively, you could just keep this line and push it outside of the box and clear the collision. So it's up to you which method you wish to choose. A possible cursor position in a CFC program is indicated by default by a gray shadow when moving the cursor over the elements. So once you have these boxes, input, output, etc., and you hover your mouse around these boxes, then, for example, when you come at this box, which is one output, you will see this gray shadow. As you could see here, we have the gray shadow, and this is the default. As soon as you click on one of these shadowed areas, still before you release the mouse button, the area will change color to red. Okay, so you click on this, it will change color to red. As soon as you release the press mouse button, this will become the current cursor position, the respective element or text being selected and displayed red color. So this is basically a selected element, and you could move all the box. You could move all the box around by keeping your finger on the left bottom of the mouse. There are 3 categories of cursor position. I know that these slides could be slightly confusing at this point, but when it comes to example and you start to make your hand dirty with the programming, you will see that all of the stuff that you learn so far will fall into the place, and you will learn exactly what we mean by these cursor position categories and etc. Okay, so it's not really rocket science, I could say. These are practical software tricks, I could say, that you will learn it quickly as you start to program. Okay, so what is the first one, the first cursor position? So we said that there is we have three cursor positions. The first one, if the cursor is positioned on a text, it is displayed blue shaded and can be edited. The three dots button is available for opening the input assistant. So for example, here, once you click on that, this is one input, you will see these three dots. Then you click on three dots and you will see the input assistant. You could select from input variables, or you could basically click more and write directly the name of the variable that you know. Primarily, after having inserted an element, three question marks represents the name of the element, which must be replaced by a valid identifier. So if you click on this, you will see this three dot, it will turn to blue, and you will choose a name, a proper, basically, variable. After that, the tooltip is displayed by positioning the cursor on the name of a variable or a box parameter, which contains the type of the variable parameter and, if exists, the associated command in second line. Possible cursor position and two examples of selected texts are displayed here. So again, you will see that when you hover around, that by default is gray, then you will click on that and it will turn to blue, and these three dots will appear, and you could click on this three dot button and select from the input assistant your input, and then you have your defined inputs, outputs, and boxes. For now, what I suggest you is that just listen to the video or read the slides, go forward until you reach to the example, or you could basically skip to the example and start basically reading over the previous slides and practice it inside the software. Okay, two other possible positions of the cursor. If the cursor is positioned on the body of an element, box, input, output, jump, label, return, comment, connection mark, this will be displayed red color and can be moved by moving the mouse. We discussed this before, and you will practice it in the software. If the cursor is positioned on an input-output connection of an element, a red field quad will indicate that position, point of connection. So these quads here, okay, and can be negated or set reset. Possible cursor position, gray shadow. An example of selected output input positions, red quad. So these are selected ones, and if you just hover around that, you will see the gray one, okay. And you could basically negate one input or set, reset it, and etc. once you select it. Okay, so it was all about the cursor. Now we move to CFC elements toolbox. The graphical elements available for programming in the CFC editor window are provided by a toolbox. This one, which comes with the CFC editor plugin. So once you choose a CFC programming language, you will see this toolbox. The toolbox can be opened in a view window by command toolbox, which by default is in the view menu. The desired element can be selected in the toolbox and inserted in the editor window via drag and drop. So you simply drag and drop input and you will see the input element. Then box, you will see the box element, and so on and so forth. For the other one, jump, label, return, composer, selector, and other ones that we will discuss in coming slide. What are these exactly? And if you wish any time to back to the pointer, just click on the pointer. Besides the programming elements, there is an entry pointer by default at the top of the toolbox list. As long as this entry is selected, the cursor has the shape of an arrow, and you can select elements in the editor window for positioning and editing them. Okay, so once you, for example, select label, if you wish back to the pointer, and then you need to click on the pointer. CFC element. As you notice in the CFC toolbox, we had a list of CFC elements. So we try to cover each of them one by one. After the cursor, we had the control point. A control point is needed to fix a manually modified connection line routing so that the modification gets not reverted by command route all connection. By two control points, you can mark a definite section of line for which you want to modify the routing. So basically you select the input output points and you will do some modification. Input box that you could send the inputs variable to your function blocks or programs. The text offered by three question marks can be selected and replaced by a variable or constant. The input assistant serves to select a valid identifier. So you click, it will turn to blue. You will see those three dots, and then from three dots you select your input output variables from the input assistant. So you need to already define those variables. Box. A box can be used to represent operators, functions, function blocks, and programs. The text offered three question marks can be selected and replaced by an operator, function, function block, or program name. The input assistant serves to select one of the variable objects. In case a function block is inserted, another question mark will be displayed above the box, which must be replaced by the name of the function block instance. If a function block with constant input parameters is instantiated, then the box element shows a field parameters. In the bottom left corner of the box, which leads to a dialog for editing the input parameters. So again, you need to basically select the box and then click on the question marks and select one instance of the already defined function blocks and programs. And again, when you start programming, all of these will be more clear to you. Then we have jump. The jump element is used to indicate at which position the execution of the program should continue. This position is defined by a label, see below, to replace the text offered by question mark by the label name. A label marks the position to which the program can jump. In online mode, a return label for marking the end of POU or Program Organization Unit is automatically inserted. It's very similar to the jump and label we used before in ladder logic program. Return, or again similar. Note that in online mode, a return element is automatically inserted in the first column and after the first element in the editor. In stepping, it is automatically jumped to before execution leaves the POU. Composer is used to handle an input of a box, which is a type of a structure. The composer will display the structure components and thus make them accessible in the CFC for the programming. For the purpose name, the composer likes the concerned structure by replacing three question marks by the name and connect it to the box instead of using and input element. We'll have example of this composer in coming slides. Selector, a selector in contrast, the composer is used to handle an output of a box which is of type structure. The selector will display the structure components and thus make them accessible in the CFC for the programmer. For this purpose, name the selector like the concerned structure by replacing 3 question marks by the name and connect it to the box instead of using an output element. We will have a selector example in coming slides. Comment, use this element to add any comments to the chart. Select the placeholder text and replace it with any desired text. You obtain new line within the command line, Control plus Enter. So those comments won't be executed, just comment, yes? And connection mark source and connection mark sync. You already have seen that how we could have a question mark by right clicking on connection line and choosing connection mark. This is one way, or you could replace and connect them or associate them together manually. Connection marks can be used instead of connection line between elements. This might help to clear complex chart. For a valid connection, a connection mark source element must be assigned at the output of an element and a connection mark sync at the input of another element. Both marks must have the same name, no case sensitivity. Naming the first connection mark source element inserted in a CFC by default is named C1 and might be modified manually. In its counterpart, connection mark sync replace the 3 question mark by the same name string as used in the source mark. So basically they should have the same name. The editor always will take care that the marks names are unique. If a source mark's name is changed, automatically the currently connecting sync mark name will be renamed also. So if you change the source name, don't worry about the sync names. The sync names will change automatically. However, if a sync mark is renamed, the source mark will keep the old name. Okay, so you should be careful about this one. This shall allow to easily reconfigure connection. Removing a connection mark also does not concern possibly existing counterparts. To use a connection mark in the chart, drag it from the toolbox to the editor window and then connect its pin with the output input pin of a representative or respective element. Alternatively, you can convert an existing normal connection line by using the command connection mark, right-clicking and choosing basically this connection mark. This command, vice versa, allows to change connection marks back to connection line. So you've done this before, and you could also revert it back to the connection line by doing a similar action. Input pins. So by the input pin, you could add 1 pin to the existing box. Depending on the box type, an additional input might be added. For this purpose, select the box element in the CFC network and draw the input pin element on the box. So you see from the picture, it's clear that how you could add 1 pin. Output pin, depending on the box type, an additional output might be added. For this purpose, select the box element in the CFC network and draw the output pin element on the box. Okay, so we went through all the elements in the CFC toolbox. It was a long definition for each, but now with these examples, everything will become more clear. So start to open the codices and start a new project and follow these examples. Okay, so I'm gonna go through the examples, but it will be, I guess, more efficient if you do it by yourself, as I'm explaining these slides. A CFC program handles an instance of function block, func block. Okay, so this is what you name it, which has an input variable structure one or stru1 of type of a structure. Again, this is the name that we are giving to this. By using the composer element, the structure component can be accessed. Okay, so or input variable for the function block is a type of a structure, but how we could feed the inputs of those structure by a composer. For now, let's start by defining the structure. The structure stru1 or stru1 has two components. You could name whatever you wish, but if you want to follow these slides and avoid confusion, just use the same name for now, okay? One of which is integer and the other one is a string. Okay, so in the app, on the application, right click, add object DUT, data unit type, okay? Choose a structure, give it a name, and click add. To declare the structure, you need to add a data unit type object to your project. Specify a name for the structure and add it to your project. Okay, now you have a structure. This is basically, you see the structure, but is empty. You need to add your variables to your structure. Declare the structure1 variable as below. Note that the object appears in the project tree as well. So you will see that here, and you need to add these two lines. So ivar, again, is the name that we choose. It's a type of integer, and the structure variable is the type of string, and it's hello. Okay, so we're gonna add word and say hello world. The aim of the function is to add 2 to the integer part and append word to the string part. So we want to add word and say hello world. Add a function block to your project, select st. Okay, so it's important. Okay, so add a function block. Okay, right click, choose POU, and then function block and programming language st, define input and output variables and implement the function. How you could define input output variables here. Okay, input, you wish to choose this structure, and the outputs, you have two outputs, one integer and one string. Okay, and here you have the program. So since you choose ST or structure text language, now you could basically have your program, main program of the function block here. So function block output integer is a structure variable dot ivar, which is the integer variable of the structure plus 2. So whatever integer you feed into the function block, it will add 2 to that number. So if you feed, for example, number 2, then the output will be 4. And function block output, the string, will be concatenating the uh, the string part of the structure, okay, hello, and the FP variable that you define here, void. Okay. This is a function block. This is one example here to start with programming of CFC. Okay, now you have one function block, and in the main PLC programming environment, we want to use CFC. Okay. In the main program, declare the variable. Here, you declare variable, insert the box, and assign it to the FB that you have created. Okay. Name it function block underscore 0 or any other name. This is one instance of function block. Insert a composer here and assign it to the structure that you have created. You assign it here. Insert inputs and outputs to complete the program. In order to connect items to each other, click on the output of one. Then drag and click on the input port of another block. Okay, so just connect them from one to another. Run the program, force the input variables, and observe the functionality. Okay, see what you will get in the output in the ERG1 and ERG2. So, for example, if you choose 2 here, you will see 4, and you should see hello world here. Example of selector. So the previous was a composer. A CFC program handles an instance of function block 02. This is again one instance of the function block and the name that you are giving to that instance, which has an output variable FB out of type of a structure. By using the selector element, the structure components can be accessed. Add the structure1 DUT to the project and declare the variables in the structure. Okay, so you have the structure here and very similar to the previous one. Here you have your function block. Add the function block to the project, declare the variables, and implement the function. Okay, so you see that the output here is the type of structure instead of input. This is the difference between this function block 2 and the previous one. According to the implementation, the integer part of the output variable is obtained by multiplying the input variable fb_in and the constant fb_in and adding fb_var. Okay, so it's basically the function here. You could change this function to whatever you wish and examine your program. The string part of the output variable is obtained by concatenating the fb_in tree and fb_var two strings. Okay. Again, this is one example to get your hand dirty with CFC programming and how, for example, to use input output selector composer blocks and boxes, and to see different cursor status. Example of selector. Let's continue with the previous example. In the main program now we want to use CFC, declare the variables, insert the box, and assign it to the FB that you have created. This time you have function block 02. Insert a selector and assign it to the structure that you have created. Insert inputs and outputs. These are inputs and outputs. To complete the program, run the program, force the input variables, and update the functionality. Okay, so if you manage to complete these two examples, then you are almost familiar with the CFC programming environment, and you could continue with other examples and exercises. Okay, now let's go to a more complex example in the CFC environment. The aim is to construct a simulated program for the program editing and data control exercise shown below. using CFC programming. Okay, so we have the ladder logic program here. You see lots of inputs and outputs, but the logic is, I think, is quite easy, except that this counter op block. So you see that we have reset, negated, and the normal contact and coils. The required variables according to the program are declared here in the main menu. So you start with the declaration of your variables, all the inputs, outputs, switch 1 to switch 6, and push button 1, push button 2, and pilot light 1 to pilot light 5. Okay, and you have also one constant here, which is preset value of the counter, which is 10. So now look at the program that they implemented in the CFC program. What I suggest you is to put these two slides side by side, print them, or you could basically divide your screen and to have two slides at the same time, and see, for example, how we are implementing the same logic. For example, when we have S1 and S2 in series, then we could use AND block, and then we have a pilot light 1. Okay. The most complex one coming from this part, um, I think you could easily get it when you put basically these two slides side by side and compare them together. I strongly recommend you to implement it in Codesys to see how you could program it. Another example, this is another example generating a square wave using timers with adjustable frequency and duty cycle. Again, you start with defining your variables. For example, TON0 and TON1 are instance of on-timer variables. Duty cycle frequency are basically real variables, large real variables. Constants again, and you already had one example or a couple of examples of these annunciators or flashers in a ladder logic program, how you could use two timers and use output of one timer as the input of the others to create those flashers or square waves. This is implementation in CFC, could be um, slightly confusing, I could say, at the beginning, but again, try to first implement it in ladder logic and then go to the CFC and see how you could interpret the CFC implementation here. So these are basically math boxes. Okay, so dividing, multiplication, substitution, subtraction, sorry, and basically converting from real to time. This is converting from type real to time. Okay, so this part looks complicated, but is not really. It's just because you want to have a different frequency and duty cycles. But if you want to have a fixed duty cycle and frequency, you could avoid even this part and go directly for setting preset values or constant preset values here. But the main part is here. You have two timers, timer 0 and timer 1, and you see that you are using the output of one for the input of the other, and output of the other one for the input of the other one. And then you have two preset time value that for the start, you could start with the constant numbers. You don't have to go with these basically complex box. Okay, it's not that complex, just looks complex, I could say. But it's meant to have different frequency and duty cycle. Again, this is for conversion from real to time. Okay, so in the previous example, you managed to program an annunciator with the CFC programming, but now you may wish to observe the changes of the output and see if the annunciator works properly. So in this slide, we will explain how you could have or trace the outputs and plot them. So sometimes it's useful to observe the changes of a specific variable over time. Add a trace object to your project as shown below. So here, right click on the application, add project, and click on trace. Specify a name for the trace. So here, so you choose your name for the trace, whatever you wish. Specify a name for the trace and add it to the project. Okay, and then click here add. Now you could observe the output. So it's very similar to the scope, for example, in MATLAB simulation. It's just a plot that you add to observe the outputs. Right click on the trace and choose trace configuration. So this is the trace, and you right click and then you choose trace configuration. Click on add variable in the right in the top right corner of the trace. So here on the top right, you select the add variable to determine the variable which you want to display. Browse for the variable name. So unlike MATLAB simulation that you could connect your scope to the output, here you need to choose a variable to trace or plot. So here you have another tab for the trace, and you click on these three dots to select the variable, and you will be able then to plot that variable. You can change the default setting for different properties of the trace for this variable here. Okay, so you could change the color or the line type and etc. here in this window. So for example, for the previous example, we wish to trace or plot the downbeat of the timer, the first timer. So select the downbeat of the second timer. Select the downbeat of the second timer as the desired variable. So click here and then go for the second timer, TON1, and click on Q. You will see the selected variable in the trace configuration window. You could also trace the downbeat of the first timer. You will see a very similar plot as you expect. Then here just click OK, and you are done with the configuration of the trace. You need to configure the trace before using it. Click on the configuration on the top right corner of the trace, then click on the task in the menu. Select main task and click OK. So here click on the configuration here and select the main task here. Save the program, log in and run. At first, you will not see anything displayed on the trace. To make it visible, right click on the trace and select download trace. So you need to right click and click on download trace here. After you run the program, so you need to log in and run the program, and after that you need to download the trace. Use the scroll of the mouse to zoom out the time axis to see the trace in a better way. So at the first glance, you might think that there is nothing here to see, but you need to zoom out. There are several options regarding the trace which are accessible from the menu, which appears by right-click on the trace. You can save the trace, load an already saved trace, and some other tasks. Change the frequency and duty cycle and check the trace. So here in the main program, you could change the frequency and duty cycle that we already discussed and run the program again and see the differences between the output and see if you could see the reflection of changes like a frequency and duty cycle in your plot. Okay, so we are done with those examples, and now you almost know how you could write the program by CFC. Now it's time to program yourself. This is the first exercise, CFC exercise, two-lane traffic light control. Write the CFC program to implement the traffic light control system. In the visualization, use sliders to change the present time values. So you already programmed the two-lane traffic light control by ladder logic. Now it's time to do it with the CFC program. So you could use the same program and try to convert it to CFC. Another exercise is a garage door control. Create a project that controls a garage door as follows. Open door button causes door to open. So motor up direct indicator. Open LED will flash with 2-second period and 50% duty cycle. And open photo eye stops the opening. Pressing stop or close door during opening will leave door stop and jar. Motor off indicator, a jar light to flash at 1-second period and 50% duty cycle. Close door button causes door to close. Motor down indicator, close LED will flash with 2-second period and 50% duty cycle, and open photo eye stops the opening. So what I recommend you to do at the beginning, try to eliminate the details of the program and implement the overall structure of the program by start stop button and basically the open photo eye maybe, and then you could add more detail. For example, open LED flashing for 2 seconds and the period of 50% duty cycle. So those details could be added later to for the sake of simplicity and help you to start with the overall structure of the program. Once you have that fundamentals, then you could add more details to the program and enhance it to the more advanced level. So this is basically a good flow chart to help you how you could program the garage door control by CFC programming. Initialization, you see that for different scenarios, how you could open and close the door or jar the door. What are the basically different scenarios that could happen here? So here you have open and door close, or here you have door open and close. And here you have between, okay, so you are ajar, so you are between opening and closing. So it could help you to do the programming. Do not rely only on this flowchart. Try to start with your own flowchart and program it by yourself. And finally, another exercise ingredient mixing process. Design a PLC program to implement the process of mixing two ingredients, A and B. The mixing cycle can be summarized as follows. So here you have the tank, the mixer, one valve for ingredient A and the other valve is for the ingredient B. And finally, you have the third valve, which is the solenoid tree, to pour the final product into the finished product tank. Ingredient A is sent to the tank first by energizing solenoid number 1. The flow meter gives 1 pulse for every gallon of flow. So here, this is a flow meter. Okay, so solenoid valve number 1 will open, energize until 200 gallon have poured in. So okay, so you need to open this valve until you have 200 gallon of material A. After ingredient A is in the tank, 300 gallon of ingredient B should be added. The process of adding ingredient B follows the same procedure as that of adding ingredient A. Okay, so only the amount is slightly bigger. We have 100 more gallons of ingredient B. After ingredient B is in the tank, the mixture or the motor here starts and runs for 5 minutes. So we need to mix them for 5 minutes. After the mixing is complete, solenoid number 3 should open and let the mixed batch go into a finished tank. Only for okay, so we need to pour all the material into the tank. Okay, so all the batch should go into the tank. When the tank is empty, as indicated by the NC empty liquid level switch. So this switch basically could send a signal and say tank is empty. Solenoid number 3 should close and stop the cycle. So now I think you know the process. The process is first to add 200 gallon of ingredient A, then stop, then add 300 gallons of ingredient B. Once you have both of them, then the mixer motor starts for a certain amount of time, which is 5 minutes. Okay, so for 5 minutes we mix them all together, and after that we need to pour all the material into the tank. Once it's done, the solenoid tree will be closed. So do these 3 exercises and submit them into the Moodle.